Hello, everyone. Welcome. Thanks for joining our diagnostic training session today. And what you're about to see is a pre-recorded training session we did over in the United States. But be assured that a lot of the material that we cover is really applicable to any automotive application. So just be aware that yes, it is a lot of North American vehicles, but they will apply a lot of the same principles apply over in the UK as well. Now, if you do have any questions, if you're watching this during the premiere, you can just leave it in the chat. We'll be monitoring live chat. If you're watching this after the premiere, then just feel free to leave a comment underneath the video and we'll get to those as we can as well. So my name is Jason Gabrenas. I'm one of Snap-on's diagnostic technical trainers. I've been in the training department since 2013, traveling around North America, helping techs and shop owners get the most out of their diagnostic equipment. Before I did that, it was a couple years as a diagnostic sales rep at Snap-on, so I had 30 different franchisees I worked with, as well as the shops that they serviced, in order to help everyone get the most out of their diagnostic needs. Then before I did that, it was 8 years at Subaru. So I worked in a dealership, and over time, I guess, just became the default diag guy in the shop. So I always ended up having the drivability problems, the intermittent problems, the weird wiring problems that would show up on those cars. And that's really where I cut my diagnostic teeth, was trying to figure out all those weird head scratcher type cars that would come into my bed. Then before that, a bunch of other miscellaneous wrenching jobs. Been a little over 25 years under hood experience for me. So today we are talking about current probe testing, checking amperage and current flowing through a circuit using a low amps probe. So first off, if we're going to talk about amperage, we need to hopefully understand a little bit better what amperage is. So amperage is a measure of the effort it takes to perform a task for an electrical component. So if it's a solenoid, I need to use this many amps to open and close the solenoid. So how much do I use? You would often hear that as current, and then the value that is used to denote what current is called amperage, right? So you've heard an amp probe or a current probe, same thing. Voltage is related to amperage, and it's a measure of the force of the electricity. So how much push we have behind it. So in the automotive world, 5 volts, 12 volts, 14 volts. Whatever that happens to be. And then, of course, they're both related to resistance as well. Resistance is the restriction or the load on the circuit, right? So a component itself could have its own resistance, or the circuit itself could have some sort of resistance. It has an inherent resistance to begin with, but it could also have additional resistance that can cause trouble in the circuit, maybe some corrosion or a frayed wire, something of that nature, right? So they are all related together. And down here on the bottom right-hand corner is Ohm's law. So that I is the current, and then voltage divided by resistance. So current is voltage divided by resistance. And the more resistance we have, the more current is required to flow through the circuit. And the voltage could drop off in that way as well. Now, if we talk about the different tools of the trade, we talk a lot about this one in the middle there, the low amp probe. That is probably one of the more common accessories added to any of our tools with the scope. Measures up to about 60 amps. Now, when it comes to the other two probes, I'd call this maybe more of a medium amp probe because it has a 40 amp scale and a 400 amp scale. And then on the left-hand side, we have what we'd call a high amp probe. It starts at a 400 amp scale, goes up to a 2000 amp scale, and it is capable of handling 600 volts DC. So if you have something high enough like that is needed, to be able to measure that, you can measure it. Now, you will notice on the low amps probe here in the middle, the two banana clips or banana jacks are separated, so you could use it on different channels on the tool. These two, though, these are actually made to work with our meters, but they will still hook up to the scope. So you'll notice how the banana jacks are stuck together. The spacing on the scope is correct, though, to plug those in. Should be able to just plug them right on the top ground in channel 1. And it would work for you. Now, the other thing, if I'm using the low amps probe and I'm using the scope, I can just put it on an amp probe setting and it'll do the conversion for me. On the high amp and I guess the medium amp probe, if you want to call it that, those need to be put on a voltage setting, and you would need to do the math in your head or write it down as to what the conversion is. Because what they all do, the commonality between all of them is that they output a voltage when they see amperage. Now, how do they see amperage? When current flows through a conductor, copper wire in this instance usually, when it flows through a conductor, it will generate a magnetic field. In all of these amp probes, there is a coil, round coil there, coil there, coil there. You notice if you ever open one of these jaws up, you can see there's a connector, and that connects the two sides of the coil when you open it up. But that coil will pick up on that magnetic field, and it'll generate a voltage out of this probe. Now, it's not a huge voltage, milliamps, but they also have batteries inside them too that allows them to amplify that and send it out to the tool as a voltage signal. So it's if I recall, on the low amps probe, it's 10 millivolts per amp on the 60 amp scale on that one, on the low amp probe. So it does generate a voltage. Also, they are directional. The amp probes are directional. I don't know if you ever take a close look at a low amp probe, but you see it's got an arrow right there. So with the current, when the current flows in the same direction as the arrow, you will see a positive number on the screen when you're looking at the scope. So if it's flowing in the same direction, it'll generate a positive voltage out of the probe. If it flows in the opposite direction, you'll get a negative result. So you'll see a negative amperage coming out. Now, you could have negative amperage in the real world if you have a problem with something, but normally you want to see a positive result, right? You want to see it going up on the screen. So in that case, all we need to do is either flip it over. If we can't flip it over because of constraints of space, because it is a little thinner on one side than the other, then we can also go into the scope and hit the invert button on that channel and flip that upside down, and that'll get us the inverted positive waveform that we're looking for. When it also comes to amperage and resistance and voltage and such, how do we know a circuit can carry a load as well? We need to think about that, because that is directly related to how much amperage that a circuit can carry. So let's do a little bit of a thought experiment, I guess you could say. So let's take a battery cable. Take one little thin strand of wire out of that multi-stranded battery cable. No, not very thick. If we connect an ohm meter to either end of that strand of copper wire, what are we going to get for a reading? Well, we should get pretty much 0 ohms, right? Because there should be very little resistance in there. There shouldn't be, you should have direct continuity between both ends, right? So that would be expected. What if I took the rest of that battery cable with all the other strands in it, put my ohm meter on either end? What am I going to get for a reading and resistance? Should also be 0 ohms, right? Because I'm going to have that direct connection between both sides. But how do we know, if we're just using an ohm meter to check circuits, how do we know that that circuit can carry a load or amperage? So we think about that single strand of wire on that battery cable going to the starter, let's say. Will 100 amps go through that one single strand of copper wire? Probably not. And if it even tries, it's going to get really, really hot. That's probably going to melt because of the amperage trying to flow through it. It's trying to pull that amperage through this very restricted wire. That's why as we increase amperage load, works the same as electrical wiring in a house or in a car. The more amperage we need to flow through a circuit, the thicker the wire needs to be because of resistance. So we want to make sure that we are testing not just with an ohm meter. We want to be able to measure the amperage, and also we want to load the circuit as well. If we're testing something, an example like this, where we have a frayed wire, you might not know. Let's say I have a bad ground and I'm testing it with an ohm meter, and I have one little strand of that wire left going to ground. My ohm meter is going to tell me, yeah, it's good. It's a good circuit. But then you try to put a load through it, it's not going to work. So a lot of folks, what they'll do too is maybe they'll test the circuit with a light. They can take an incandescent light bulb, like out of a old headlight bulb or something like that, and plug it in and see if it's bright. If it's bright, then the amperage can flow, and we know it's a good circuit. Otherwise, if it's dim, then we know that it can't flow through, and it's a bad circuit, frayed wire, right? So just take that into consideration, because all of this kind of goes together, right? On the amperage and resistance and such. So let's talk about a few tests that we can do with our current probe that we're talking about here. First one's a fuel pump current ramp test. Now, I know I've talked about this before, but it's always good to refresh. And what you want to do is, if you have a snap-on scope, tool with a scope in it, it's going to have guided component tests available in there. The easiest way to do this is to just pull up the guided component test for your particular car and do a current probe test or current ramp test. All you have to do is place the jaws around any wire, a wire, the power feed wire or the ground wire, somewhere in the fuel pump circuit. If you can get close to the pump, that's great. Clip it around the wire there. If you can't get close to the pump, because we know most cars it's on top of the tank and there aren't any access holes on some of these cars. Sometimes there's a fuse. If there's a main fuse that goes to the fuel pump, you just pull the fuse out, put a jumper and put it around that. Same thing with a relay. If we can't get to the fuse or the fuse powers multiple things, go to the fuel pump relay, pull the relay out, put a jumper in and check it there. We want to just have it around one wire somewhere in the circuit. And what we're going to see is we're going to see the current flowing through the circuit through the commutators and brushes inside that fuel pump. Now, most automotive fuel pumps are going to have 8 commutators in the motor, and that's what allows it to spin. The brushes stay stationary and the commutators spin around. So 1, 2, 3, 4, 5, 6, 7, 8 commutator segments on this particular pump right here. And then we see a worn out bunch of commutator segments over there. So over time, they wear out, the brushes wear out. And internally, the windings can also wear out. So when we're doing this test, we should see something like this. Each one of those bumps represents one commutator segment in that motor spinning by. You see the current go in and then up and down and up and down. You see that ebb and flow on the pattern. You want to make sure the bumps are fairly rounded and there aren't any missing. So in this case, about 79,000 miles on this car at this time, and it's got a little bit of a shark fin look to it. So it is starting to see a little bit of wear there in the pattern. Normally would look much more round than it is there. You want to make sure there aren't any missing. So let's say, for example, this one right here, this one with the little fuzzy thing on top. Let's say that one's just missing, gone, flat. This one's missing, gone, flat. That would indicate a bad commutator. And a bad commutator can cause an intermittent no start. So if we think about it, it's spinning around and spinning around and it stops on a good set of commutator segments. I have a good circuit there. I can just, when I go to start the pump, it'll start right up because the current's able to flow. Then it stops on a good one, it starts right up. Stops on a bad one, then current can't flow through the coils and it won't get it to move. Now, those are the kind of no starts you fix with a hammer. You tap on the bottom of the gas tank, right? And then it vibrates that fuel pump enough so it spins around to a good one. Then when it's on that good commutator segment, it can spin right up. Now, when it's normally spinning at its normal operating RPM, yeah, maybe it might spin a little bit slower, I suppose, but the kinetic energy of it spinning around pushes it past the one with the bad connection. So it doesn't really affect it too much when it's running. But it's like playing roulette, hoping it doesn't land on the bad segment, right? So we want to measure that and check. So if you suspect you have that problem on a vehicle with a customer complained an intermittent no start, that may be the cause. So you can always go check it out with that current probe and make sure that it's working. Now, if you count out 8 bumps, that's one time around to the motor, because we said most fuel pumps, most automotive fuel pumps, non-brushless, so brushed automotive fuel pumps, have 8 commutator segments. So in this case, if we count out 8, that's one time around. So we got 1 there, 2, 3, 4, 5, 6, 7, 8. Then number 1 over here again. So that is one time around, and then the pattern repeats. I can see I got that little fuzzy guy there. I got that little fuzzy guy there. That's the pattern repeat. Right. So if we know that, that's one time around. You can also calculate the RPM of the pump, which is important to know because the RPM of the pump controls the volume. Speed of the pump controls fuel volume. Pressure is controlled by the regulator. So we want to make sure we have good volume if we have a drivability problem. Now, if you put it in a 10 millisecond window, like it does automatically in the guided component test, if you see at least one time around, which we do, that's going to be 6,000 RPM. If it's more than one time around, it's more than 6,000 RPM. If it's less than one time around, it's less than 6,000 RPM. Rule of thumb is a good fuel pump is going to run 5,000 to 6,000 RPM or more. When you get down to 3,000 RPM or less, you're going to have that fuel delivery problem. So on this pump, we see it turn 1.5 times in a 10 millisecond window. If I was going to eyeball this, we know one time around is 6,000 RPM. We get another half time around is another 3,000 RPM because 3,000 is half of 6,000. So add those two up, it gets us 9,000 RPM. Things screaming right along. Now, if I wanted to do the math, whoever told you had to do math when we're working on a car, but yeah, some things it's good to do math with so we can figure this out. So if we use those previous cursors, And we use the delta time. So that's going to be the distance in time that it took to travel around once. So we're going to look at the measurements at 6.95 milliseconds. One revolution on the pump takes 6.95 milliseconds. Now there's 60,000 milliseconds in a minute. So we take those 60,000 divided by how long it takes to turn one time, we get the RPM of the pump. So 60,000 divided by 6.95 gives us 8,633 RPM on that pump. That is very close to what we eyeballed on that previous screen. That is within 5%. So that's close enough for my camp. So that's a good fuel pump. It's 8,600 RPM. Now let's talk fuel injector current ramp. So we talked about the fuel pump current ramp. Now I'll talk about a fuel injector current ramp. This allows us to see the mechanical operation of the fuel injector as it opens and closes, because a fuel injector, a standard gasoline fuel injector, it's going to be basically a solenoid, right? It's going to electromagnet in there, pulls a pintle up off a seat, and allows it to open and spray fuel. So we see this is a pattern that has voltage from the circuit. So that's the injector driver. Line voltage comes in, pulls it down to ground to open it, and then when it closes, we see a spike. And then on the green line, we have the amperage flowing through. So when it opens, when it grounds the injector to turn it on, this is the amperage flowing into the coil and the electromagnet in there. We also see a little bump right there. We'll talk about that in a second. And then when the injector closes, we see it drops down. So if we want to look at that closely, here's a standard top feed gasoline fuel injector. Got constant power from the battery, and then it's grounded by the injector driver inside the computer. So when it does ground it, we see the voltage flows in here and the amperage flows in here. So the amperage increases. What we want to see is a nice smooth ramp like this. And then when it closes again, it's going to close quickly, and then we see the amperage go away. We want to see a nice smooth ramp up here. In this case, it's a current limited design, so it looks like maybe when it gets to about 1 amp or so, it levels off. Other designs can go up continuously until it closes, looks like a triangle. So it can work either way. What we want to pay attention to in this case, other than we want to see a nice smooth ramp, if it goes up sharply, that indicates a problem with the windings inside the injector. And we'll see an example of that on an ignition coil in a second. But we want to see a nice smooth ramp. What we see right here, this dip. This dip is the point where that pintle actually opens and the fuel starts spraying, because we have to charge that coil first. So we're going to have a little bit of current going in there to charge that coil before it moves. Once it does move, we see a little dip. Now, it's important to watch, especially if you suspect you have a mechanical issue with the fuel injector. If it's opening at roughly the same time every time it opens and you're watching one fuel injector at a time, then that's in good shape. But if it opens here, there, everywhere, and it seems to be opening it erratically, kind of randomly doing whatever it wants, that indicates a bad spring in there. It's just kind of rattling around in there. It's not opening and closing at the same time every time. So that's an indicator of mechanical damage, bad spring inside. So that is fuel injector, right? Fairly straightforward. Now let's look at a coil. So the coil test is very similar to our fuel injector test because they work on a very similar principle. They have coils of wire inside. So all we have to do is take the power feed to the coil. This is a coil on plug vehicle. Take the power feed to the coil, put our low amp probe around that, and see what we get for a pattern. Same thing, right? Comes in, 0 amps. This will be the part where coil starts charging. So we call that the dwell time, right? So as it dwells and as it charges the coil, more and more current flows in, more and more current flows in. In this case, this is also current limited. So about 12 amps looks like. And then if it wasn't current limited, it would come up like a triangle and come down. But in this case, it is current limited. And then when the coil fires, we get that rapid decrease of amperage in the circuit because all the voltage has left the circuit, so the amperage leaves as well. Once again, we don't want to see a sharp uptick and over. We want to see a nice smooth ramp like this. If I wanted to compare that to a secondary ignition pattern, we can see how the current ramp goes up, and we can see where dwell starts and dwell ends right here when it fires, right? So we can see where there's where dwell starts, amperage starts, dwell ends, amperage ends, right? So you can see how they tie together like that. So let's look at a bad coil example. So there's an example of a BMW that had a misfire, and here's the coil pattern that they got while checking with the guided component test here. And we can see the known good pattern up here. Well, that's supposed to look like a triangle. That doesn't look like a triangle, right? We have that sharp increase in current before it actually goes over and starts making that ramp. So that indicates an issue with the windings in there. If we expand it, we can see it a little bit taller, a little bit better. High amperage, about 8 amps before it really starts kind of leveling off there. And then we see about 11 amps up to 12 amps. That actually increases every time it strikes. This is what they call a multi-strike coil. So it actually fires multiple times per an ignition event. So in this case, we see that big jump in current, and then it jumps back and forth over there. So they said, well, that's definitely bad. We have some bad windings in there. So let's replace it. So you replaced it, and of course, as good technicians, you would want to verify that solved the problem. So they checked it again and verified that it did indeed solve the problem. It had a good pattern here. Now we do see a nice smooth ramp. Triangle in this case, not current limited, gets up to about 10 amps or so on the first firing. And then each successive firing, we see it goes up, and it's fairly level. Maybe goes down a little bit, down to about 8 amps down here. Now on a multi-strike coil, you will see that high amperage on the subsequent events, not the first one. You want to look at the first one, but any second and subsequent events that happen there, it's trying to overcome. There's already energy in that coil that needs to be dispersed. So it needs to have higher amperage to overcome that. And so it just goes back and forth. We do see it's a much sharper ramp on all of those successive dwell events right there. So that is a good coil on a multi-strike card. All right, and then relative compression. So let's talk about a relative compression test. This is kind of a cool little test we can do. We think we may have a mechanical problem with the vehicle. One of the cylinders is low. Maybe I got bad compression. How do I check that? Well, let's see. I can take out the compression gauge, pull the plug, screw it into the cylinder, crank it over, see where it reads, write it down, go to the second cylinder, see where it reads, write it down, and so on and so forth, right? You can probably do that in like a minute and a half, right? Probably not. It's going to take you a while, pull all the plugs and do all that, especially depending on how the engine's configured. If you can't get to the plugs in the back, if it's a transverse mounted engine, that might be a challenge. So instead, we can actually use our scope and a current probe to do a test to see relatively cylinder to cylinder, how does my compression look? So here's just an example cranking over. This is fully zoomed out. If we zoom in a little closer, we can see here is our relative compression test on this vehicle. Now, I forgot to tell you how it works. So how it works is we use the starter, which is a heavy electrical load on the engine. So it's got to spin that engine. What's it fighting when it's spinning the engine? It's fighting the compression that's in the cylinders already, right? So the more compression we have, the higher the amperage draw for the starter. So if I have lower compression, I will have a lower peak because it won't be drawing as many amps. If I have higher compression, it will be a higher peak because I'm drawing more amperage. So what you want to see, ideally, on an engine that's good, you want to see them fairly consistent across the board. In this case, we have a 6-cylinder. So channel 1 is our amp probe. Channel 2 we have hooked up to, looks like probably a coil. And we can see that is, call that cylinder 1. Right, so 1 and whatever the firing order is, but we see every other cylinder is low. So in this case, this truck, this Jeep, was a Jeep, was a V6 Jeep, ended up having a bad cat on one side. Couldn't increase the compression in there because we couldn't get it out. So it had a clogged exhaust, clogged cat on one side. It had lower compression events on that side of the vehicle. Now, sometimes if I have just one cylinder, that's a problem. I would have one cylinder that's lower than the others, right? So we can do that using a low amps probe. You can also use it with voltage, and there's also some vehicles that support it in the scanner and automated test as well. Like Ford's the one that comes to mind, but this one works on any vehicle. It's pretty universal. As long as we know the firing order and as long as we can establish what cylinder is what on the screen, that'll help us in order to understand where the problem might lie with the vehicle. Then the last one we're going to talk about, last test we're going to talk about before we go live on the tool anyway, it's going to be parasitic draw. That's a pretty popular topic always as well, especially with all these newer cars with all the modules on there. Well, you have one module that stays awake too long and drain down the battery. So you want to be able to find out where, if there's a draw in the first place. And then after that, you want to be able to see, well, what's causing the draw, right? So here's an example of a parasitic draw test. Did that right from guided component testing as well. And we can see on this car, this is just as a car was shut off. As a car shuts down, the modules will go to sleep depending on how many modules it has. It could take some time to put those modules to sleep. There's actually a way we're going to show you can force certain vehicles, you can force the modules to sleep. But once the modules are all asleep, then we need to establish, well, what is the draw on the battery? What's the baseline draw? Because they do still draw a little bit of current to keep memory alive and things like that. So in this case, this is a vehicle shutting down, had 200 milliamps, and then you see that module, whatever that draw was, turned off, then it went down to about 100 milliamps or so, and then eventually over time settled down around about 50 milliamps. Now, rule of thumb for a draw on a vehicle, about anything under 50 milliamps on an older vehicle, couldn't really tell you a cutoff here, but less technologically advanced vehicle with not so many modules, about 50 milliamps. The more advanced we get on the vehicles, more modern vehicles can be anywhere from 85 to 100 milliamps is still considered an okay draw on a battery nowadays with a vehicle off. So just be aware of that. So 50 milliamps across the board, you'd be pretty good. If you see 85 milliamps and it's a fairly recent car with a lot of different modules on it, that's probably okay too. Because you got to think about it. If I got 20 modules on a car, that's all going to add up. Even if it's just a couple milliamps a piece, it's going to add up after a while. All right. So we want to make sure that we understand it. 50 is not the tried and true anymore. It can be a little bit higher than that now. So just keep that in mind as well when we're looking for a draw. Now, how do I know what's on if I do see a draw? Well, if all of a sudden it's set at 50 milliamps and it goes up to like 300 and the key's off and keys out of the car. Oh, yeah, by the way, when you want to do this, if you have a car with a fob, get the fob away from the car too, because the car is going to continually try and ping that fob to try and find it as well. So you got to make sure you get the fob away from the car. That's a pretty common complaint I've heard from customers. They walk in the house and they turn around and they put the key fob hanging right next to the door. What's on the other side of the door in the garage? Well, it's their car. It's only maybe 10 feet away at most. And they wonder why their battery goes dead if they leave it over a long weekend. Well, it's because it kept the car awake because the car thought the key was real close. You want to keep the key as far away from the car as possible, especially when you're doing a test like this. So how would I figure out what circuit is going? Well, we might want to use another tool, maybe a thermal imaging device, right? So here's an example of a thermal imager, and we have a couple relays right here that are on. If current is flowing, not only does it generate a magnetic field, but it also generates heat due to that magnetic field. So we should be able to see either a hotter fuse or a relay or something of that nature warmer than the rest. Because remember, with a thermal imager, it's not always hot, cold. It's a relative scale, right? It could be 10 degrees warmer or 5 degrees warmer, but it may still show up on the screen because we're looking at a differential between the two. So that's just one way to look. You can start pulling fuses and see if it drops as well if you really wanted to do that. But if I can direct myself to the fuse I need to pull faster, that's going to make my life a little bit easier as well. All right. I've talked well enough about theory. Let's go and look at it in practice. All right. So first off, I want to talk about, I did mention earlier that on certain vehicles, you may need to shut down the systems because it takes a long time to go to sleep. I think maybe about a year ago, we actually added a function in the scan tool for BMWs. So I got a 2018 BMW 5 Series here. And this definitely has it because I checked earlier. So what we want to do is, well, there's a couple ways we can go about this. We can go directly to the module and have that turn it off. I'm going to go back to category view here. We can go directly to the module and turn that off. If I have a tool with my service resets and relearns, it's also in there. But I'm going to show you how you would get to it through the system itself. So we're going to go find that as a body control. So I went past it already, right? There you go, body control. And that is in what we call a body domain controller. I'm going to go in there. I'm running a simulator, but that's okay. And it is under functional tests, of course. and it is a special function. And we see sleep mode right here. So what this does is with the power down command, the vehicle is brought to a rest state within a short amount of time. So instead of taking a long time, could take 15, 20 minutes, half an hour. I'm not really sure how long it takes, but it's a long time. So it'll turn things off quickly so I can do, say, a parasitic draw test or something like that. So to switch off terminal 15 or pad mode via actuation command, send the power down command, go to sleep a bus system and switch off terminal 30 after a short after running period. Notice the deactivation of terminal 30B can be detected from the switch off of the hazard warning switch light. Do you wish to send the power down command? You hit continue, and it would power down the vehicle. It's going to look just like this. It's going to send the command, say functions complete. You could actually probably see that on the scope too. You just watch the amperage drop very rapidly, and you'd be in the low milliamps at that point. So that's kind of a neat little functional test we can do with that. What else can we do? I'm going to go into, if you have one of our tools with the scope with a guided component test in there, so that'd be a Zeus, a Verus, Modus, a Triton, or a Vantage. If you go into guided component tests, first off, with the current software, they moved the training and classes up to the top, and they just call it classes now, just so you know. If I go into classes, I have power user tests in here. So I can do current probe tests, and I need to select my current probe, either a generic probe, because you can use any probe with it, or the old probe or the new probe. So we're going to the new probe, current ramp testing. Then it talks about fuel injector, parasitic draw, fuel pump, ignition coils, and a manual. All right, so how about parasitic draw testing? This is where I went to do that parasitic draw test. Now you can walk in there, clamp the current probe around the battery supply wire, or the negative battery cable, or the positive battery cable. Either way, somewhere in the circuit, so I can measure the amperage flowing through it. So that's current probe testing in power user tests. We could also go into into how to, and there's a wealth of classes in here too, talking more about what we discussed this evening. So for example, 10-minute battery drain test class. Let's see, 10-minute electronics classes. In here, we have things like what is amperage? I'm gonna walk through it. Diode continuity, electrical circuits, voltage drop test, Ohm's law. Ohm's law is really good because that'll tell you about the relationship between current and voltage and resistance. All right. Variable resistors, voltage, scientific notation, etc. So if you want more information on any of those topics, it's built right into your tool if you have one of those tools already. Let's see, internal combustion engine, running compression waveforms, electric, different windows, things like that. All sorts of different tests in here. There's over 65 different categories of class inside. And then, of course, if we have a vehicle, I'm just going to pick one here. I'll just pick our tried and true Tahoe here, 16 Tahoe. And under my guided component test, I can go into engine. And let's see, I have, where is it? Fuel system. So we can go into the fuel injector. There's a current ramp test there. It's going to walk you through what it's supposed to look like. Right, so there's a single injector and there's a group of injectors. If you check at the fuse on the injectors, if they have a common fuse or a common relay, you can see all the cylinders on the screen at the same time. So as long as you know the firing order and you know which one is which, if one is too high, there's a problem. If one is missing, there's a problem. Right, so you can walk through and being able to visualize the current flowing through that circuit will help you narrow down what you need to diagnose. Fuel pump. Right, I talked about RPM calculations and things like that. Well, that's in here too. So if I go down a little bit, fuel pump RPM calculation, right? Most fuel pumps run about 5,000 to 6,000. Drivability symptoms below 3,000, just like we said. And then here's my calculation right here, 60,000 milliseconds in a minute divided by how long it takes to turn one time. You get your RPM, right? So you don't need to memorize all of these math problems we're telling you here either. All right, so that is, there's a lot of stuff you can do with a current probe to help you out, speed up your diagnostic process. So hopefully you've learned a few little tips and tricks that will speed up your work when it comes time to check some of these electrical problems. And with that, that is our time here today. So make sure you tune in for new diagnostic content every week. We will be premiering a new video every Wednesday at 7 p.m. UK time. So make sure you check it out on the YouTube channel. If you're watching, well, of course, you would be watching this on YouTube, but make sure you subscribe, thumbs up, ring the little notification bell so you know anytime we post new content. And it's youtube.com/Snap-on Diagnostics UK. With that, time for questions. If you have any questions, just feel free. Once again, if you're watching this on a premiere, just leave it in the live chat and we'll answer those. Otherwise, leave a comment under the video and we will get to those as we monitor those comments as well. So I'd like to thank you for taking a little bit of time out of your day to learning a little bit more about how you might be able to be more efficient at diagnosing vehicles using some of the information that we've given you today. Hopefully, we'll see you next week. Hopefully, you can watch and see you on any of our other videos. Have a good week, have a good night, and take care.